Good morning. Well, it's really early morning here. I don't really do mornings very well, and so I don't really know how well this is going to come off. But I just woke up. But we need to start talking about Chapter 6, so I guess we'll go there. So Chapter 6 deals with electrons and electron configurations. In other words, how the electrons are arranged around the outside of an atom. So I guess your first question might be, why do I care? Why do I care? I know that a calcium atom has, say, for example, 20 protons, because its atomic number is 20, which means in a neutral calcium atom I've got 20 electrons. Are those 20 electrons just flying around all over the place and I don't really know where they are? In a manner, yes. But there are places where they're more likely to be. So how are those 20 electrons arranged around the atom? Well, that's what we're going to talk about here. Why is that really such a big deal? Well, I guess it's nice to know for knowledge's sake, but there's a more practical reason why we're talking about this. Let's say, for example, I have two atoms and they're going to react. Well, if they're going to react, they've got to touch. If they don't touch, they don't react. If I have a piece of zinc and I put it in a beaker over here, and I have a hydrochloric acid over here, it's not going to react until I put the zinc in the hydrochloric acid. Well, if they don't touch, they don't react. Are they going to want to touch? Well, this is surrounded by a negative shell of electrons, and this is surrounded by a negative shell of electrons. And I know that like charges do what? Well, they repel, right? So what I've got to do is I've got to force them together somehow. Okay? And that extra energy I have to add to force those atoms together is part of something called the activation energy, which is the amount of energy you have to add to a reaction just to get it started. Once I get them to touch, then the electrons are going to interact, and I'm going to get myself a chemical reaction. Well, do you see that if I know how the electrons are arranged around this atom, and I know how the electrons are arranged around this atom, particularly the outer electrons, because that's where they're going to touch, then that gives me some sort of insight into how they're going to chemically bond together. And that's really what I'm after as a chemist. It's nice to know things just because you do, but see, I can start making predictions of how things react if I know something about electronic structure. And that's important to a chemist, because when we mix beaker A and beaker B together, we like to know what's going to happen. Is it going to fizz? Is it going to turn green? Is nothing going to happen? Is it going to explode in my face? I like to know things like that before I mix them together. My wife really likes surprises. I'm one of those people that, I just tell me what you're going to get for Christmas, and I will tell you if that's what I want or not. I'll give you an idea, go buy it, and I'm happy. She likes to be surprised, and so I have to come up with a new one every year. And she may like it, she may not, but she just likes the surprise. Chemists hate surprises. Surprises get you killed if you're a chemist. So you like to be able to know at least an idea of what happens before you start mixing things together. Sometimes you are pleasantly surprised. Sometimes you are unpleasantly surprised. But it's always better to kind of have an idea of what you're doing when you get into the chemistry lab, because not knowing what you're doing can get you killed. So that's why this chapter is really important. 99% of this entire book deals with the electrons. Chemistry is all about the electrons. There's only one chapter in the entire book that deals with the nucleus. And we'll talk about that somewhere down the road. All right, but it's really all about the electrons, and that's why that's so important. Okay? Okay, well, let's go to chapter 6 then. All right, if I told you what I need to tell you right now about chemistry and the structure of an atom, you honestly probably wouldn't believe me. So what we're going to have to do is we're going to have to back up, and we're going to have to do a little bit of background before we get to where we need to go. So let's go back to the 1800s. We're going to go back that far, I guess. But before we do that, what we need to do is we need to talk about waves, all right, and some things that you can measure in a wave, and then we'll move on from there. So little bit of background information. Let's talk about something called the electromagnetic spectrum. The electromagnetic spectrum, there are all sorts of waves of light that are whizzing by you every day. And the thing is, you can only perceive a very narrow portion of that spectrum. Most of the stuff that is kind of whizzing by you, your eyes can't pick up, and you don't know is there. Kind of makes you paranoid, doesn't it? All right? So all the wavelengths of light that you can see and that you can't are part of what we call the electromagnetic spectrum. And light can be considered a wave. So that means we need to talk a little bit about waves. So what are some things we need to know about waves to be able to discuss this in a logical manner? Well, first thing we need to talk about in a wave is something called the wavelength. Okay? The wavelength is the distance from crest to crest or trough to trough in a wave, or really just one repeatable unit. So for example, here's a wave. And so it's a nice repeatable, it's a little sine wave like this. Okay? The wavelength would be the distance from crest to crest, so here to here. Or I could have measured it from trough to trough. Or I could have measured it from where it's going down here to where it's going down here. All those distances are exactly the same. Okay? It's the distance of one repeatable unit of the wave. If I have a very long distance, that's a longer wavelength. If I have a very short distance between the two, then it's a very short wavelength. All right? And that's one thing that you can measure. The second thing you can measure about a wave is something called the frequency. And the frequency is the number of waves passing by per unit of time. So let's say, for example, it's summer, and you're at South Padre Island, and you're sitting on the beach, and chemistry is over, and you're watching the waves come by from the ocean. So you have absolutely nothing to do, and so you're counting the waves that are hitting the shore. And so you sit there with your little watch, and you watch for a minute, and 30 waves hit the shore in a minute. Well, you would have a frequency there of 30 waves per minute. Okay? And frequency is given by this little crooked V, which is nu. Okay? And it's the number of waves that pass by per, in this case, second. There's a relationship between the wavelength and the number of waves passing by per second for electromagnetic radiation, because all light travels at exactly the same speed in a vacuum. Now that's not necessarily true of all waves, like sound waves and so on and so forth, but in a vacuum, light travels at 2.998 times 10 to the 8 meters per second. 10 to the 8 meters per second. All right, that is the speed of light in a vacuum. Nothing can go faster than the speed of light in a vacuum. It's kind of the cosmic speed limit. All right, and we give that a letter, and that's C. And C pops up in a lot of calculations, and that's what it's equal to. That is a constant that would be given to you on the test. Okay? So, does it make sense to you that if the waves are traveling at the same speed, and I have a very short wavelength, then I probably have very many waves passing by per second. If I have a very long wavelength, I have very few waves passing by per second, because the speed is exactly the same in a vacuum every single time. So there's an inverse relationship between the two. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. Right? And that's given by this little equation right here. Nu is equal to C over lambda. Okay, notice the inverse relationship. Had a analytical chemistry professor said when people come up to him in college and ask them what's nu, they say C over lambda. Horrible joke. But here's the thing. You always remember the horrible jokes. You never remember good jokes. You always remember the bad jokes that people told you. So what's nu? C over lambda. Notice this is in meters per second, so that means my wavelength here is going to be in meters. My frequency will be in inverse seconds, or per second. This many waves passing by per second. Third thing I can measure about a wave is its energy. How much energy does the wave have? Well, that's usually measured in joules. The energy of the radiation is proportional to the frequency. Okay? In other words, the higher the frequency I have, the more waves passing by I have per second, the higher the energy. All right? And so we come up with this little equation, E is equal to h times nu, where h is Planck's constant, and that's 6.626 times 10 to the minus 34 joules seconds, if I remember correctly. That's a constant that would be given to you on a test. If E is equal to h times nu, and nu is equal to c over lambda, then it follows, here's another equation which is going to come in handy, and that is E is equal to h times c over lambda. See, all we did is we just substituted in c over lambda for nu there. And that gives me a relationship between the energy of a wave and its wavelength. Notice it's an inverse relationship there because that wavelength is in the denominator. So if I have something with a very short wavelength, that means a very high frequency and high energy. If I have something with a very long wavelength, then that means low frequency and that means low energy. Inverse relationship between the wavelength and the energy. Well, as we said, let's go back to 1800s actually. Okay. So in the late 1800s, there was a fellow by the name of Lord Kelvin. Yeah, that Kelvin, temperature guy. And he was making a speech, and he kind of famously said, everything in physics is already known. All that's left are decimal points. In other words, you know, we know it out to the 4th decimal place, and maybe if we're lucky, in about 20 or 30 years, we'll know it out to the 6th decimal place. But it's pretty much been done. Well, you know, when you make statements like that, sometimes it comes back to bite you. And it did, you know, for Lord Kelvin. Because at the end of the 1800s, we didn't understand it, but things were about to get really, really weird. We realized we didn't really know as much as we thought we did. Okay? And that's kind of where we're headed. So give me a little bit of time in the 1800s, and maybe we'll make it up to 1900 here pretty soon. All right? Okay, so we did kind of know things. There was a theory that worked really well for short wavelengths. And there was a theory that worked really well for electromagnetic radiation that worked well for long wavelengths. But here's the problem. The theory that worked for long wavelengths was horrible for short wavelengths. The theory that worked for short wavelengths was just absolutely awful for long wavelengths. So we didn't seem to really truly understand electromagnetic radiation really, really well. All right? So let's talk about the electromagnetic spectrum here. So what is the electromagnetic spectrum? Well, as we said before, there's all sorts of wavelengths of light whizzing through the room right now, and your eyes can only perceive a tiny portion of them. All right, so what are those anyway? Well, that little tiny portion of light that you can perceive is something called visible light. And what the wavelengths of that light tend to be somewhere between about 410 nanometers to about 760. That's a good range. Depends on your eyes. I guess some people can see better than other people, right? But that's the wavelengths that you can see. What does nano mean? Well, that's 1 times 10 to the negative 9th of a meter, nanometer. Do you remember that? We talked about that earlier, and we said remember that one because it would come back somewhere later. That would be here. Okay, so very, very tiny wavelength here. All right. What wavelength is hitting your eyes, you actually perceive as color. The light hits your eyes, hits the rods and cones in the back of your eyes. Your brain, your little digital signal, well, it's an analog signal processor, I suppose, starts interpreting things, and it says, we're going to call that red today. Okay, we're going to call that orange. So the shortest wavelength, highest energy light that you can see is violet. Purple, basically. All right. The longest wavelength, lowest energy that your eyes can perceive is red. And all the colors of the rainbow here are basically just certain wavelengths of light. and your brain changes those into colors. That's how it works. All right? Well, turns out there are wavelengths of light that are higher in energy or shorter than wavelength than what you can see. And there are wavelengths of light that are lower in energy and longer in wavelength than what you can see. So let's start going shorter in wavelength, higher in energy first, and then we'll head over toward the other side. So wavelengths that are higher in energy, shorter than violet light, now you're into what we call the ultraviolet spectrum, or the UV spectrum. Where do you get ultraviolet radiation? Well, it comes from the sun. Okay, this is what causes a suntan. It's just light that is shorter in wavelength and higher in energy than visible light. All right, are there wavelengths even shorter than the ultraviolet spectrum? Well, yes. Now you get into the X-ray spectrum. All right, so what do we use X-rays for? Well, X-rays, yeah. If you break a bone, what you do is you shine X-rays through your arm, let's say, for example. X-rays are strong enough that they can actually penetrate skin and tissue. They'll just go straight through. But things that are extremely dense, like bone, they're not strong enough to penetrate. And so, therefore, what happens is you shine X-rays through. What you get is the X-rays go through, they hit photographic film over here, although nowadays it's all digital. And that develops the plate over here or whatever over here. If it hits the bone, then it stops it, so you get a negative. You get a dark spot where the bone is and a light spot where it goes through. And then you can turn that negative into a positive, and that's what an X-ray is. And so you can see pictures of broken bones and things like that. Are X-rays good at looking at things like muscle sprains or tissue damage? Well, no, because they go straight through. If you want to look at that, you need something like an MRI or a CAT scan or something like that. But for broken bones and things, X-rays, dental, teeth, X-rays will do a really good job. Could I just take a flashlight and shine through my arm and looking for a broken bone that way? Well, no, because your arm is massive enough there to stop the visible light. So what you get is you get a shadow on the other side of your entire arm. You don't get a picture of the bones. So yeah, you need to do X-rays there. So yeah, I think we're all pretty familiar with X-rays and kind of what they do. All right, shorter in wavelength and higher in energy than visible light. Now you're into the gamma ray or the cosmic ray spectrum. Your book is called Cosmic Ray Spectrum. And these are very high energy waves. You can put your hand out to stop a gamma ray. It will go right through your hand, right through your body, cook your internal organs on the way through, and just exit out the other side. Very high energy short wavelength radiation. These mainly come from either radioactive decay, which we'll talk about someday, or they come from certain cosmological processes in outer space. The Earth is actually protected by the ozone layer, which is one thing, but also by a magnetic field. And so that kind of filters out quite a bit of the radiation. And we actually live in a fairly quiet corner of the universe. There's not a lot of radiation flying around. We kind of live in a cul-de-sac, I guess you could say, which is a good thing, because otherwise we'd all be dead, or we couldn't go outside. So yeah, it's kind of a quiet neighborhood. All right. Okay. Well, if there are wavelengths of energy of light shorter in wavelength and higher in energy, are there wavelengths of light that are longer in wavelength and lower in energy than visible light? Well, yes. So let's talk about the other side of the spectrum here. So wavelengths that are longer and lower in energy than red, now you're into what we call the infrared spectrum. What's another name for the infrared spectrum? Well, infrared radiation is a fancy name for heat. It's what heat is. Heat is light that is longer in wavelength than what you can see. What do we use infrared radiation for? Well, all sorts of things. We cook our food. We keep warm with it. Just all sorts of things that you can use infrared radiation for. The little thermometers that you push the button, it goes up to your forehead like that. It's measuring the amount of infrared radiation coming off of you, and that's how they measure temperature without sticking that mercury thing in your mouth and so on and so forth. So yeah, lots of uses for infrared radiation. Night goggles that Army uses, things like that. What they do is they actually shift the infrared radiation spectrum over to the visible spectrum, and so you can see things at night. You can see living things because they all generate heat, so you can see where people are in the dark. So that's how that works. Wavelengths that are longer and lower in energy than infrared, now you're into the microwave range. So what do we use microwaves for? Well, cooking. A microwave oven. By the way, wavelengths at this point, somewhere around a foot, just to kind of give you a reference there, I guess. But that's the microwave spectrum. All right. Microwaves, you can put your food in a microwave and it will cook faster than if you put it in a conventional oven, right? Well, which is higher in energy? Well, infrared radiation is higher in energy than microwave. So why is the food cooked faster? Well, you're bombarding your food with microwaves, but it's not just any microwaves. It's a certain frequency or wavelength of microwaves. And that particular frequency, a water molecule happens to absorb, and it happens to cause those water molecules to vibrate. And so when those water molecules vibrate violently, what happens is they heat up. And when they heat up, that cooks your food. So in a microwave, what you're doing is you're cooking your food, and you're cooking it from the inside out. And that's a lot faster than cooking it from the outside in, which is what you do in a normal oven. Because you got to get through that first initial layer of whatever, and then you got to cook the core, and by the time you cook the core, then it's done. In a microwave, everything cooks pretty evenly because you're cooking from the inside out. And so it's that specific wavelength of microwave is why microwaves work faster. So yeah, you can cook things a lot faster in a microwave, but are there downsides to that? Well, yeah. You ever had microwave pizza? Absolutely horrible, right? Just comes out all chewy and doughy and yuck. Okay? Microwaves don't work well for cooking pizzas because in a pizza you want a hard outside crust. You want the outside to cook quite a bit and the inside a little bit less. And so ovens work really well for pizza. Microwaves don't work so well. But popcorn, microwaves work great for popcorn, and they work really great for heating things up. So most kitchens have a regular oven and a microwave because you want them to do different things. Okay? But that's what microwaves are. They're just wavelengths of light, even longer and lower in energy than infrared. Longer and lower in energy than that, now you're into the radio spectrum. Okay? What do we use radio waves for? Well, communications, yeah. Your cell phone. Your cell phone is a radio transmitter receiver. Cell towers all over the place. And then there are certain frequencies that each particular company uses, that's how you communicate, text-wise and voice-wise. TV, those are actually radio waves that are sent, out to the nation there. Radios, when you tune into a particular radio station, say for example you listen to 102.1, Kiss FM or something like that. Basically what that is the frequency. 102.1 FM frequencies or radio stations are measured in megahertz. So 102.1 means there's 102.1 million waves, radio waves, passing by you every second. Quite a few. All right. If you're listening to an AM station like 550, maybe you like talk radio, AM are measured in kilohertz, okay, which means 550 means 550,000 waves passing by per second. All right, but that's what the frequency are. It's the wavelength that the information is encoded on, and therefore the frequency, the number of waves passing by per second. Those are radio stations. The government controls the radio spectrum because you don't want everybody broadcasting on the same frequency at once. You ever try to listen to 6 people talking at once? It's kind of hard to hear, right? Well, imagine if you turned on your radio and 6 different stations were all talking at once. These 4 stations were trying to play a song. one station was trying to do sports and the other was trying to give you the news, you never hear anything. And so the government says, oh, okay, you can broadcast here, you broadcast here, you broadcast here, and that way everybody can hear. All right. And cell phones, same way. They sell spectrum, sell frequencies that cell phones can use, and they charge a lot of money and make money off of it. And supposedly, presumably, that comes back to us somehow. You know, who knows? That's politics. We won't get into that. But yeah, that's what the government does. Shortwave radio, you know, your ham radio operators, the old guys, those radio waves are extremely short, very high energy. Longer wave radios, microwaves, sometimes they use into the microwave spectrum. They use for telephone communication cell towers, analog. You know, that they blend lines. They'll send over, then have a receiver, and then send it again until it gets to where it needs to go. But that's those are radio waves, and we use those for communications. NMR is radio waves. Probably where you've run into that, that's ours. Chemistry is probably like hospitals. An MRI. You ever heard of MRI? Stands for magnetic resonance imaging. Well, basically, it's NMR. It's nuclear magnetic resonance, but they don't like to use the word nuclear in a hospital because it scares people. But basically, they hit you, they put you inside a big giant magnet, and they hit you with a frequency of radio waves, and then your little nuclei in there will spin flip, and then relax, and then they will send off a radio signal. And then the MRI gets that radio signal back, and you can actually make a picture of your insides tissue because of the water in your tissue. So MRIs work really good where X-rays can't because you can look at pictures of soft tissue now and you can see what's wrong in there. But yeah, it's that's what we use radio waves for. All right, and all those wavelengths make up what we call the electromagnetic spectrum. And of all those wavelengths, you can only see a tiny, tiny portion of those flying through the room right now. Okay, well, we're coming up on 30 minutes here, so let me introduce a particular problem we had back in the 1800s, and then hopefully maybe we'll try to solve it in the next video. So it's late 1800s, and we know that when we burn certain elements, they give off all sorts of pretty colors. You know, this is how fireworks work. You know, you have gunpowder, but what makes the red and the green and the yellow and so on and so forth, different fireworks, is metal impurities in there, not the gunpowder itself. That's how you get color. We know that certain elements burn certain colors. People have known this for, centuries, millennia. Okay? But why? Nobody knew. All right? And here's the interesting thing. When you burn certain elements, they give off certain colors, and it's characteristic for an element. Why is that? Well, it turns out that all elements, when you burn them, only give off certain discrete wavelengths of light. In other words, they don't give off all the colors of the rainbow. They only give off some of the colors of the rainbow. And so what we have here is something called an emission spectrum. In other words, these are the colors that they give off. The opposite is the absorption spectra. In other words, they're wavelengths of light that certain elements absorb. But that's, same thing as this, just opposite, really. But yeah, here are your emission spectrum. And notice, instead of seeing a continuous spectrum like this, what you see lines. And what these lines represent are wavelengths of light that particular element gives off. And notice that each particular element has different wavelengths of light that it gives off. And so what this is like a fingerprint. Each of you has your own little fingerprint, and it's totally different from everybody else in the classroom. Well, each element has its own fingerprint, different wavelengths of light it gives off. And that's why they burn different colors. Now, if I can distinguish each of you from your fingerprint, well, I can distinguish each of these elements from their fingerprints. And that's something called AA, or atomic absorption spectrometry. You burn it, you look at the wavelengths of light coming off, or you look for certain wavelengths of light coming off that are distinctive with a lamp, and you can identify whether there's sodium in my sample, or hydrogen, or calcium, or so on and so on and so forth. So atomic absorption spectrometry, really good at analyzing particularly metals. If I have a metal analyzed, that would be a really good way to do it. All right, and so yeah, there's some utility there in the chemistry lab for this stuff. All right, but here's the problem. Number one, why do different elements give off different colors? Number two, why do elements only give off certain wavelengths of energy? Why don't I just get a continuous spectrum? Why is it only for sodium this wavelength, that wavelength? That's a doublet. Well, don't worry about it. It has something to do with the magnetic field. Not important. This wavelength, this little doublet here, probably actually has two singlets just close together, and this wavelength right here. Whereas hydrogen here and calcium's a more complicated spectrum. See, what's up with all that? Well, that's where we're headed. A fellow by the name of Niels Bohr decided to study this back in 1880. And that's where we're going next. We're going to talk about what Niels Bohr, the theory he came up with to explain all this, does it work, and why we care. But I think that's a pretty good place to stop. So we'll stop there for now. We'll pick up in 1880, and then hopefully by the third video, maybe we'll be up to 1900. All right? So we'll see you next time. Bye for now.